Good morning, everyone. Welcome to AskSelva 013 on Power System Studies. We are on 2nd May 2021, 10 a.m. Indian Standard Time. Thank you so much for joining on time. If you are able to see my screen and if I am loud, please type out loud and clear in the chat box. Thank you so much, Vaishya. If you are able to see my screen and if you are able to hear me loud and clear, type out loud and clear in the chat box. Let me move forward. So thank you so much for the followers in YouTube, LinkedIn, Facebook, Google review and Instagram. Thank you all. Good morning, Satya. So this is what we are going to see today. Why 3.7 kilowatt motor should not be connected directly at PCC, that's a power control center or a primary control center. Then why it has to be considered or connected in MCC. That's a question from Yusuf to a comment box in AskSelva 4 which he has posted. So I'm just thought of taking that question first. Then probably we just go little more onto transformers, and if you have noticed our Tech Thursday where we have written how the transformer loading and how the kVA rating of the transformer. So we will try to answer a basic question why transformer is rated in kVA. Then we also answer a question how much it can be loaded, and at the end we will wind up the session with few ETAP tips. Good. So you're able to hear loud and clear. Thank you so much for that. Let's straight away jump to the first question. But meantime, if you are able to answer any of the questions in the chat box, like why transformer rating in kVA or why transformer is rated in kVA, some basic questions. If you have the answer, kindly post that answer in the chat box so that the session will be more interactive. Why transformer is rated in kVA, or how much we can load that, what factors influence the transformer rating, and probably if you have gone through this tech article what we have written on Tech Thursday, you can elaborate more onto that. Right, good. So I'm expecting few answers. Yes, correct, but something about loadability and load encroachment. I'll take up that question along with maybe a distance protection when we are going to deal probably in the few weeks to come. So we'll take up this load encroachment along with this distance protection. And I'm not really sure what you mean by loadability. You can elaborate a little more on that, and if relevant, like we can also take that topic. But I guess like load encroachment, what you're talking is with respect to the distance protection zone 3, right? Yeah, transformer load is not dependent of load. That's an answer, I guess, for why transformer is rated in kVA. Okay, all good. Fine. So let's go ahead and answer a question of the first one. Why transformer, why motor of 3.7 kilowatt should not be connected to PCC, and why it should be connected to MCC or distribution boards. So let me take a typical 11 bar 415 volt transformer. Take a typical 11 bar 415 volt transformer. Can you say like what could be the maximum transformer rating which we can go with 11 bar 415 volt transformer? Let me give the voltage so that you can see that. I guess even if I am in ETAP, you are able to see my screen clearly. The numbers are visible, I guess. I have done my maximum possible zoom. So if you are able to see this clear, then that's great. All right, good. So now I have a 11 bar 0.415 kV transformer. What could be the maximum rating of the transformer? Any guess what could be the maximum rating of the transformer? Yeah, thank you Charinath for answering it. Because of a high short circuit if connected to the PCC. Yeah, even if the PCC short circuit level is high, but means why we should not connect the motor? What's the problem with connecting a motor of 3.7 kilowatt to this PCC? So let me name this as a PCC. Few people name this as a PMCC, right? So that's also fine. Yep. What could be the maximum rating of this transformer when it is connected to 11 kV on one side and low voltage like 400 volt or 380 volt or a 415 volt or 480 volt? It depends upon which country you are from. So when one side of the transformer is connected to low voltage, what could be the maximum transformer rating, and what's the factor which limits that maximum transformer rating? Yeah, thank you, Parthiban, for putting up 2.5 MV as an answer. Thank you so much for that. Like, let's try to understand more why we should limit the transformer rating to 2.5 MVA. 2.5 MVA really not a constraint, but we will see like what are the factors which is probably pushing us more or less close to 2.5 MVA, right? So even 3.5 MVA transformers are available at 415 volts, but probably means what say we can understand from maybe one or two scenarios. If I am means what say increasing this transformer to an example say 10 MVA, right? So that probably answers the question. I have increased the transformer to 10 MVA. So is this okay to have 10 MVA transformer which is connected at 415 volts? Answer is probably I'm expecting answers. Shall I connect a 10 MVA transformer which step downs the voltage from 11 kV to 415 volt? Right? Yep. Waiting for few answers. Right. So let me probably means highlight some area so that probably you can understand why we cannot go for a 10 MVA transformers. So if you take 2.5 MVA transformer, on the 11 kV side the full load current is 131 amps, and the LV side the voltage, that is 415 volt side, the current is 3478 amps. 3478 amps is the full load current. And probably if it is a 10 MVA transformer, then it will be just a 4 times. That's well known. Like the full load current on the 11 kV side is 524 amps. I guess that numbers are visible. If not, like you can go to the maximum screen and you can watch that, right? So the current is 524.9. I guess you're able to see that numbers, right? Yep. And the full load current is on the LV side is 13,912 amps. What is wrong with that? If I go with the low voltage circuit breaker, unfortunately, we do not have a circuit breakers more than 6,300 amps. So, which mean the breaker rating, continuous current rating which is available on the LV side breaker basically dictates what could be the maximum transformer rating which we can go with. So if you take power circuit breaker, probably you can go with reputed manufacturers and try to find out who is the probably means what's the maximum rating which is available, right? So you can find maybe up to 6,300 amps breakers, and I have never seen any breaker beyond 6,300 amps in 415 volt. So basically the 6,300 amps which dictates or decides what could be the maximum transformer rating which you can connect. So let me go to an Excel sheet and address like what could be the approximate or the maximum transformer rating which can be connected is limited to, if it is a 415 volt, I have taken example of 415 volts, so I am taking that, is this. Like 4.5 MVA is the theoretical maximum, at least theoretical maximum transformer rating in kVA which we can go, correct? No, so I have put root 3 into voltage into current, that gives the kVA, or probably means what I can put that numbers like 415 kV, and current I am just putting, so and probably means what I multiply this amps. So I am trying to find out the kVA. So the limitation on the transformer rating, if it is connected to 415 volt, then it is like 4500 kVA. If it is 0.4 kV, it is like 4.3 MVA. If it is 380 volt, then it is further less. If you have 480 volt, then it could be slightly more, right? So this decides basically what would be the maximum transformer rating which can be connected at low voltage side when you are connecting. So let's maybe move on to the next topic, slightly here itself. And 6300 amps, shall I load up to 6300 amps? Yes, you can load. But if we have a transformer of 2.5 MVA, whether the LV side voltage fluctuation is it zero? Answer may not be. So what's the voltage fluctuation which is allowed? Maybe 10%. So when I go with the, like means what's in this case, like when I go with like 5.25 MVA transformer, the current will be like 6300 at 480 volt. But because of whatever the voltage fluctuation in the grid, or because of the heavy load, if the 480 volt side volt comes down, do you think that the current remains same? Answer is no. So what I am trying to mean by that, this is theoretically okay, but you need to always account the voltage fluctuation into this. So what I mean by that, like if you have like 4 and 5 volt, even though you have 6300 amps, you cannot really means what say go with 6300 amps. You may need to multiply that by uh, zero point 0.9, at least 10 percentage 10 percentage voltage fluctuation, right? So then probably means what say your rating comes down to like approximately 4000 kVA. So if you are okay with this with the 6300 amps, probably at least you can go up to 4 MVA. But this is only with respect to the full load current which I have talking so far, correct? No, this is a full load current. I am not really talking about the short circuit current. So at least we can say the full load current of the transformer should be limited less than the LV circuit breaker rating which is available. So that current is 6300 amps, and you need to consider voltage fluctuation. So you cannot really load up to that 6300 amps. That means you can allow up to 6300 amps, but when there is a reduction in voltage, the current will increase. So you are taking a 10% margin at least. People may go with 20%, but at least a 10% margin is needed. So you can have up to only maximum of 4 MVA transformer, not really beyond it. How many of you felt that information is useful and you have learned something new today? How many of you felt that information is useful? Yeah, if the information is useful, type out useful in the chat box so that I can understand, yes, that information is useful, though that's not the topic of today and the question. Right, so let's come back to this 3.7 kilowatt motor. So let me try to connect this 3.7 kilowatt motor here in PCC itself. So answer here, this 10 MVA is not really right. So means what say you can go maximum up to 4 MVA, but I mean what say going 4 MVA also you need to check other aspects like what's the short circuit current and other stuffs. Yeah, thank you Praveen, thank you Surya. So as we have seen, up to maximum of 4 MVA which we can go, and 4 MVA results in some current of this, and you can go with that kind of breaker. And probably means to say if you are going with say maybe typical impedance, which I used to refer always, you should not use typical impedance in IEC as per the ETAP, because ETAP refers to the old IEC standard, and you need to take a new reference, or probably you have to take the report from the FAT report, or how to identify the optimal tap impedance, sorry, ideal impedance of the transformer. You need to perform load flow short circuit motor starting, and you need to identify the optimal transformer impedance. Having said that, so let's probably look into the short circuit study and find out what's the fault current which may come if we have a 4 MVA transformer. What's the mistake which I have done? I have not given the grid short circuit current. Somebody has posted in one of the group like how to find out the short circuit level at 11 kVs in utility. It's not possible unless otherwise you know the upstream information, like where does this 11 kV substation is fed from, and what's the transformer rating, and what's the transformer impedance. Any industries are connected which injects the current back to 11 kV. All this informations you know. and utilities might perform load flow, and they will update the short circuit level at each and every substation every year. So let me go ahead and look at what's the short circuit current at PCC. Yeah, thank you all for giving confirmation that yes, it is useful, because I personally felt the time is the most valuable thing which you can give it to anybody else. And thanks for coming on Sunday, that too in India, like the election results. Despite of that, if you are sitting here, which means you are giving value to this, and it's my responsibility to add or give a value to you, right? So if you look at this 4 MVA transformer, if I go, the fault current is about 71.312 kiloamps. I have just gone with 4 MVA, and probably means what, say, you can put up your impedance display here, right? 8 percentage. The fault current is about 71.3 kiloamps, even without any contribution from the downstream. But really means what, say, in a downstream you will be having quite a lot of motors, so the fault current will be much higher, and even 100 kiloamps breaker may not be sufficient. And it is just not about the circuit breaker rating, but is also about the earthing requirements, right? If your fault current contribution is 71 kiloamps, and though it is not the right way to do that, but like let me put maybe the loading on the transformer is, say, example 3 MVA, you need to detailly model it, but because of the time constraints I am just putting means what, say, 3 MVA here at 0.85 power factor, assuming that 80% load is constant power loads, which is a motor loads, and 20% load are constant impedance load. This is means what, say, changes drastically with respect to what kind of industry which you are using, right? If it is a commercial building, you will be having predominantly constant current loads, like that's UPS and power electronic devices like data centers. But if it is an industry which predominantly has some motors, then always there is a probability that more than 80% of the loading on the transformer could be a motor loads, and remaining 20% could be a static loads, right? And I'm assuming also the short circuit contribution from this motor loads are 6 times, and probably means if I go, this gives worst of worst case, and to an extent probably that's what I told, like you need to model the cables, motors, the motor short circuit current, everything in detail, but that may not permit us to do all those things. Yeah, low flow is not what we need to perform. We need to perform short circuit studies. Yep. If you look at this fault current is like as high as 91 kiloamps, which means you need to go with a 100 kiloamps circuit breaker, not only in the incomer but also in all other outgoing feeders, right? At least even if you put 75 kiloamps breaker for an incomer, that's sufficient, because the short circuit contribution from the transformer is only 71 kiloamps, but you will be having multiple outgoing feeders, and at worst case, like means was a 91 kiloamps can flow if there is a fault immediately after any LV circuit break, right? So that's the real reason why, like means predominantly we limit the transformer rating to maybe 2.5 MVA. Few people may go with the 3.15 MVA, and you can go back to IEC 60076. You can go to IEC 60076 and look at what's the transformer standard ratings. It's like 100 kVA, like it starts from 25, 25, 40, 50, 63, 80, 100, 125, 160, 200, 250, 350. So it goes on. So you can pick up the standard ratings of the transformers, and you can look at typically means what, say, the transformers, or I have seen quite a lot of consulting organizations working in a steel plant limiting this maximum transformer rating to just 1.6 MVA. They will never ever allow you to go beyond 1.6 MVA. And means what, say, it has grown to 2 MVA in some industries, and typically like Parthiban has answered 2.5 MVA, that's Vaishya has answered 2.5 MVA, that's typically means what, say, Indian mindset, like most of the places we are going with a maximum transformer rating of 2.5 MVA, and I guess other countries like Singapore or even the Middle East means goes with the same standard rating 2.5 MVA in most of the cases. But there are transformers available up to 3.15 MVA, even 3.5 MVA, which I have seen at like 380 volt or a 400 volt, etc. And now assume that, like means for, say, if the load is, say, example 3.6 MVA or 3.7 MVA, then probably means for, say, you may go with like two numbers of 2 MVA transformers, which needs like a two medium voltage circuit breakers. And probably means if you are familiar with the solar farms, that case like you might be using another technique of going with three winding transformers or even multi-winding transformers, so that you reduce the number of switchgear requirements in the medium voltage. Like ETAP allows you to model only up to maximum of 3 MVA 3 winding transformers. You cannot really model of multi-winding transformers, but if you are familiar with the solar plants, even you may go up to 5 winding transformers, right? How many of you have used 5 winding transformers? Oh, so I'm just giving a 3 winding transformer. Here, if you go with a 3 winding transformer, then the typical problem is like you may not have a typical impedance, and it also gives an additional benefit like you have to find out what could be the typical impedance of the transformers, and means what say how to find out the secondary to tertiary impedance is also another other story which we can learn. Right, so that's good. So answer here like means if you want to go for higher ratings, and if your reliability requirement is not so severe, then you can think of three winding transformer. And if the plants like solar plants where the plant load factor is just about 20%, it is quite common to go with four winding transformers and five winding transformers, which means if you are taking that transformer for a maintenance, you will be completely losing all the four inverters which are connected, and you will be losing the power generation from that, but still that saves a quite lot of cost on the MV switch gears, so the capital investment is worth of it. Thank you Praveen for saying that that transformer is there at your site. That's great. Right, so coming back to this, so let me run this again short circuit study at this place as well, just to look at what's the fault current. So another mistake what we have done, we have connected a third one and we have not given the short circuit level, and means what's it, now it will run. Yeah, and probably means what's it, rather than wasting our time in a NETAP tip separately, we can go with the NETAP tip now itself. Say example, if I want to display the X by R ratio of the transformer, if I want to display the X by R ratio of the transformer, which may not be possible from here. If you look at transformer, you can display the ID, you can display the rating, you can display the voltage, you can display the tap, you can display the winding configuration, you can display the impedance. You cannot display anything else. But you can use this option called data blocks, and you can display whatever you want, either R by X, X by R, whatever you want, you can display it. So for that, what you need to do, you need to use this toggle data blocks to display on and off. And if you want to put an arrow, you can put an arrow so that you can understand this. And probably what parameters to be displayed in this data block, which you can control here by means of moving what is to be displayed and what's not to be displayed, and for various study results. So I expect you to explore more on this, and you display all necessary parameters here in data block. That's I mean what's a good way of I mean what's a presenting it. Right? You can use that's always better. That's the ETAP tip today. So don't expect an ETAP tip at the end of the session. So I have completed that now. Hope that ETAP tip what I am using this here data block editor, and for enabling data block editor you need to select what's the equipment and what's the parameter to be displayed and for what studies, and means what's it to switch on switch off here, and probably if you want to connect it with a line you can understand that line. And for that you need to ensure that this DB data block option is checked here, and I guess that ETAP tip is useful. Right, so now what we found is 57 kiloamps here is the fault current, and probably here it is 91 kiloamps, and here I have not really connected any loads. If I connect the loads, then probably the fault current could be more. So let me go back and try to add a motor. sorry, of 3.7 kilowatt. Our question today is why this 3.7 kilowatt motor should not be connected at PCC. So the answer is here. So 3.7 kilowatt motor with 415 volt. I have not used any data, like it's a typical data efficiency is like 72%. It is too less. I'm not really sure like why that is that much low. Right. We will try to find out maybe something else. Yeah. Okay. Manufacturer data is better. 82%. Yeah. 70% efficiency is too low. Okay. Fine anyway. So means if you look at the full load current, look at the full load current. The full load current is 7.33 amps. And for 7.33 amps, what could be the approximate cable which you can put up? What should be the approximate cable length which you need to consider for just a current of less than 8 amps? And probably that has to be answered with what's the current density of the equipments, and the current density of the copper or aluminum. You have to find it out. You can just check what's the current density of copper and aluminum, and you can very well try that. But I'm just going to focus more on the LV circuit breaker. The full load current, whether I have used LV circuit breaker, no, I have used contactor inside, so I need to use LV circuit breaker. Yes, right. So the full load current of 3.7 kilowatt motor is 7.33 amps, and when you're having this 7.33 amps, your circuit breaker rating should be much lower, and probably means for, so let's look at some molded case circuit breakers. You can choose whatever you are familiar with, like let me go with the ABB T2 model. That's quite famous model in ABB. Okay, I think I have to go a bit fast. Yeah. So T2, yep. So if you take like a T2, yep. So you have like a motor circuit breaker also for that, correct, no? And you need to check the right voltage. I'm sure that is 415 volt. Yep. So you know like what is magnetic, adjustable, magnetic, fixed, right? Thermal, magnetics, all of the stuffs. And definitely this need other bimetallic overload relay as well. So here if you look at this is an interesting fact to be answered. Though my full load current is just 20 amps or 10 amps, because the full load current is here less 7.3 amps. So like even you can select less than 20 amps if it is available. But okay, right? Yeah, but that's only with fixed. Yep, right. So 8.5 amps if I'm choosing, like means also you need a service and ultimate braking capability of more than more than the short circuit level what we identified at this place, which is more than 50 kiloamps. Yeah, cable length which I have not given, like let me give a cable length as well. Say maybe let me take say 10 meters, but 10 meters is too less. Let me take 100 meters. It depends like where your switchgear is placed and where your motor is connected. So let me take a 50 hertz system, maybe an aluminum cable typically used in India, and let's select the voltage of 1 kV, insulation of XLPE, and guess like means what, if you go with the 3 core, the minimum cable size itself not really, that means like you don't have the correct library there, right? You can probably means for say even means very smaller size which can carry like just 7 amps is more than sufficient. So let's not really focus on the voltage then. Let's choose the conductor alone with an insulation of XLPE. Logically makes sense. Single core cable definitely you need not go. Frequency anyway 50 hertz is what we are using, right? let's look at what could be the minimum size of the cable which we have. Yeah, everywhere this cable size is quite high. Yeah, at least 35 which you have. But even if you take 35 square cable and if you try to terminate in the motor, probably means what say the people those who are at site may understand the difficulty. Size of 3.7 kilowatt motor itself less, and the cable terminal box size is too less, and you cannot really terminate this 35 square cable which we have means what's it selected. Like if you look at what's the cable which we have selected, cable size, type and length, if I display, yep, 35 square cable which I have selected. Like let's look at some interesting size of the transformer. Yeah, not anyway going to stop it. Yeah, this could be approximately like 3.7 kilowatt, that is 5 HP motor. It will cost Indian rupees about 21,000 rupees. And you can see this cable terminal box at the top, and means what say you can imagine the size of 35 square cable, 1.1 kV, that is in India. Yes, but you can go with 1 kV grade, that is as per IEC as well. 1.1 kV grade, 3 core, 3.35 square cable. Like try to find some images, right? So this, anyway, we may not be able to get exactly for 35 square cable because we really do not know like what's the size of this. But you can imagine, like means what say if it is a 35 square cable, putting that in means what say motor cable terminal box is that not that easy. So generally you may go with maybe a 4 square cable or even 2.5 square cable might be more than sufficient to carry that current, even including considering the voltage drop. So let's probably means what say run a short circuit study again, but this time probably means with the fault current, or not only at the all the buses but also at the motor terminal, right? Let me convert this into a node to bus, right? So then let's run the fault and look at the fault current. You have interestingly noticed one important aspect, like even with the 35 square cable, what I have considered the fault current of 57 kiloamps came down to just 2.3 kiloamps, just 2.3 kiloamps. And imagine if it is a 4 square cable or 6 square cable. Imagine if it is a 4 square cable and 6 square cable, what would be the current? That current could be in few amps, not really in kiloamps. And if the length increases, the current will further come down. That's another note which you need to note. So means what say why 3.7 kilowatt motor should not be connected at PCC. PCC is rated for a short circuit current of 65 kiloamps or 50 kiloamps, depends upon the transformer rating and transformer impedance. And connecting a small MCCB of just 10 amps, you need to force that MCC to be like 65 kiloamps or 75 kiloamps based on the short circuit current. That's point number one. And you can understand also the fault current variation is huge when the length of the cable is really far, and probably means if I have modeled originally the 4 square cable where the fault current could be too less, right? And third important aspect, like let's give some setting for this, and then let's see whether this device is able to protect the cable or not. So we have given already some settings, and let's go forward and look at, right? So this is the means cable of 35 square which we have selected, but probably means for say try with maybe 2 square sorry 2.5 square cable or a 4 square cable. The damage curve will be much less, and probably means what say your protection may not be able to safeguard your cables. Here what's a cable which I have selected is heavily oversized. How can I claim that? The flow current of 7 amps can be easily carried out even by a 2.5 square cable. 2.5 square cable. If you're in a doubt, then probably means what see you can find some Catalogs. I'm just putting Havels. You can probably means who is your favorite manufacturer. You can put it because Havels I have used quite few times. At least the catalog is great. So like you can probably means want I can share that link also in the chat box. Right, so you can see like the square mm starts at single core 4 square mm. It's a 2 core cable. Like if you take 3 core cable, 4 square mm cable, correct, no? So the weight, everything we have given, like current carrying capacity is what we need to look at. 4 square mm cable can carry easily 28 amps, 23 amps, 23 amps. Even if it is an aluminum conductor, correct, the current carrying capacity is like 28 amps or 23 amps inducted air, even for a 4 square mm, and our requirement is just merely about 7.33, which mean even a 2.5 square mm cable can carry at least half of this current, and even with a derating factor of maybe 40-30%, still 2.5 square mm will do if current carrying capacity is the only issue. And you can refer this is another amazing document which you can look at. Right, fine, someone has put up some comments, I have made it visible. All right, good. So now you have understood, like means what say why we should not use a 3.7 kilowatt motor directly at PCC, because one, this breaker you need to size it for the full load current of the motor, which is too less, and which means the breaker rating itself like a 10 amps or something, and this 10 amps breaker has to be designed to cater this 50 kiloamps or 65 kiloamps or 75 kiloamps. That's what you need to really look into. That's another important aspect. And when there is a fault at the remote place, the fault current is too low, that means the current variation, short circuit current variation over the length of the cable is too much, that's a second issue. And means what to say, instead if you place this 3.7 kilowatt motor not in PCC, probably by default somewhere downstream in MCCs, the always an advantage is like short circuit current of MCC is much lesser than PCC. Like you may be having 50 or 65 kiloamps in PCC, whereas the MCC, the short circuit current is less. And means what to say, you can understand one aspect of it, like means what's the incoming current rating versus outgoing current rating. So incoming breaker we have selected 4000 amps, right? Incomer selection like full load current is like 3400 and something, right? 3478. So means you have an incomer breaker rating of 4000 amps. And what could be the highest outgoing from this PCC, and what would be the lowest outgoing from the PCC, which we can put it. So highest outgoing should not be more than like 1/3. What I mean by that, so if you divided by this by 3, means you will get 1300 amps. Like means then you cannot really means for say go beyond 1200 amps as a single outgoing feeder from this particular MV switchgear, sorry, LV switchgear, this is PCC. If you use, which mean you are means what say really not using this PCC effectively. If one single load is more than 1250 amps, then instead of like moving this PCC, you can probably means move that to that place itself. So the maximum outgoing, the ideal design, or probably the right way of designing, you should not go beyond 1200 amps for the feeder. And probably means what say similar way, like you should not means what say go anything less than say 250 amps. If needed, like you can go with maybe 160 amps, but means if you are going anything less than 250 amps or 160 amps outgoing feeder, then probably the way what you need to really look at is your uh, short circuit current withstand capability. Say example, if I'm going with the maybe yeah 160 amps feeder, or like let's look at something more. Yes. So assume that like we have means what say going to some MCC, and this MCC is say example, like you have connected load of maybe 100 amps or something, then what we need to really look at, to carry this 100 amps, what could be the conductor size which we need, correct? Say maybe to carry this current of this much, like you may need 70 square mm cable. Let's put 70 square mm cable. Yep. Let's always take 1 kV grade cable. Take always an XLP insulation, aluminum, right? 70 square mm. That's great. Assuming again 100 meters, right? Good. So here, if you look at this, I mean, the fault current and the delay time, what you need to give. So here you might be connecting quite a lot of motors. Here you might be connecting quite a lot of motors, and you need to coordinate them well. So if I'm just trying to copy this, okay, we can probably draw something new here. I'm just going with an ABB again, just to keep it in assumption that that's the same switchgear and the same manufacturer only has manufactured this. Like if I'm going with maybe T2S, and probably means also, let's say, like means 160 amps if we are going, even if you're going with, say example, means solid state release. Let's look at what could be the problem which we can anticipate or we may anticipate. Is like here we need to ensure like it's coordinated with the downstream, and probably means also at 3 times the pickup, like you are giving, say example, 0.1 second or 0.25 seconds, because this coordination has to be done with the downstream. And probably means also try to check the short circuit withstand. Few people may claim that the short circuit verification is not really needed for an LV, but that's not true. You need to validate the short circuit withstand capability for medium voltage, high voltage, low voltage, everything. But predominantly in low voltage, since the full load current is high and the short circuit current is less, it is not needed. But when you are trying to connect some cables like this, a very smaller size cables like 4 square mm cable or 2.5 square mm cable, because of that very small load which is connected with a very higher short circuit current, then obviously you need to check essentially the withstand short circuit withstand capability of this. And for that, like you might be aware another terminology, lead through energy validation for the LV cable. Yeah, you can find out lead through energy of MCCB if it is a current limiting type. Yeah, probably means other ABB example. Yeah. So this one probably means also gives you what's the lead through energy of this circuit breakers, and probably you can find it in the catalogs. What's the lead through energy? And for that lead through energy, you have to compare with this cable short circuit withstand. I guess like there is a formula which you might be using for a short circuit withstand. I guess that all given in this catalog, like minimum conductor area which has to be selected, A, that is an area in square mm, is with the formula of this, right? You can refer this, the same document which I have shared it in the link, which you can take it off, and you can say like how to size it. The same thing is applicable for HV, medium voltage, and LV. But in LV, like the current is too low. When I say current, the short circuit current is too low, and current full load current is more. And full load current, you to in order to carry this full load current, you will go with a higher size, and hence that will be easily take care of this short circuit also. That's a logic. And that may not really work when you try to have a very smaller size cable length because of a very smaller length, smaller size load, and when you have a large huge fault current. So here probably means again you can check the short circuit withstand capability of this cables with respect to this means lead through energy of this MCCB and this cable. And most of the times whenever you have a like a smaller loads current, like means if you're going with 63 amps or 100 amps, then the cable size requirement will be less, and that cable may not be able to withstand the short circuit current, especially when the cable length is too small. I guess I mean, so say there are some points which you have taken out from our presentation today. why 3.7 kilowatt motor should not be connected directly to PCC and it should be connected to MCC instead. uh, Answer is, if you connect 3.7 kilowatt motor directly at PCC, the short circuit level is higher, and though the current is only 7 amps, and in order to take the full load current of 7 amps, 2.5 square mm cable is more than sufficient. But you need to withstand and break the fault current of like 75 kiloamps or 100 kiloamps, depends upon the PCC short circuit current, which increases the cost of the circuit breaker, increase the dimension of your PCC. It also complicates the arrangement of your PCC, and overall, I mean, so say to an extent, it destroys the coordination as well. So that's the real reason why, like, you should not connect small capacity motors directly at PCC. Instead, you push the small capacity motors to downstream MCC in a motor control center. I guess that's clear. Yeah, let me look at some questions. Yeah, thank you, Praveen, for confirming you have seen a transformer. I guess that is a solar plant. DY11, Y11, Y11, Y11. Yes, all the transformers which are connected to the solar inverters are of star, and HV side that might be around 11 kV or 33 kV. And if it's a 5 winding, predominant might be it is 33 kV most of the cases. That's delta. Thank you, Praveen, for that update. And Arun Kumar, in a three winding transformer, a fault in two winding will impact the power supply and third winding. Could you please elaborate this? Arun Kumar, I guess that's a simple, straightforward answer. I guess like we have seen an image here. Yep. If there is a fault in any one of the winding, then probably means what, say you cannot really operate this transformer if there is a fault anywhere in this place, even including this cables. Like you will be having an LV circuit breaker here in the switchgear, you will be having an LV circuit breaker in the switchgear as an incomer, and you will be having CTs, relays and circuit breakers in this medium voltage. If there is a fault anywhere in between, like your breaker has to trip and isolate that, otherwise your transformer will get damaged. So it's pretty straightforward. Means if there is a fault in any one winding, it could be 11 kV, it could be like 415 volt, or in this winding, or even this cable, which I have not really modeled, but you can put it the model, because you can connect always this transformer through a cable only to the switch gears. This cable or this cable, when there is a fault, that has to be isolated. Yeah, Cherrynath, what factor decides the incomer to be MCCB or ACB? Answer, your short circuit withstand. And probably means what, say your MCCBs are available typically up to 800 amps, and like few manufacturers are giving up to 1600 amps, not really more than that. So anything above 1600 amps, by default it is ACB. Then question is like where to choose MCCB or ACB is plays a role only between like 400 amps to 1600 amps, right? Because less than 400 amps ACB is not available, more than 1600 amps MCCB is not available, and only very few manufacturers giving MCCB at 1200 amps and 1600 amps. So the debate is ACB or MCCB only at from 400 to 1600, and it depends on what you want, like whether you want to withstand the short circuit current for a duration because of the coordination, then choose ACB. If you really doesn't need to withstand the short circuit, then probably means for say, if you're okay with only the braking capability, if you doesn't need a withstand capability, then you can go with MCCB. And typically like people go like 400, 500, 630 amps, up to 630 amps people tend to go with an MCCB, not really investing heavy cost on ACB. And 800 and above people tend to use ACB always. But nowadays, like I mean, few people are I mean, so say tend to use MCCB even for an 800 amps and 1000 amps. I guess that answered your question, Sharinath. Thank you for the question. Yep. Why transformer is rated in kVA? That's another question, and I guess like we have 10 more minutes. Shall we have a quick answers for that question as well? Yeah, why transformer is rated in kVA? How much we can load? What factors influences that? We have written a beautiful article on last week on Tech Thursday. Just go to that and watch it. And I guess most of you are definitely already following us in LinkedIn, and please go for it. Yes, Praveen, that is not really the right answer, and Transformers are rated in kVA because copper loss depends on the current, iron loss depends on the voltage, and it depends on the power factor. That might what we have learned in our college, but that's not really an ideal answer for that. Transformers doesn't have any independent constraint on real and reactive power, and the capability curve of the transformer is a circle, and that's the reason why transformers are rated in kVA. If you take a motor or a generator, they have independent constraints on a real power and reactive power, but that's not the case with the transformer. Real power doesn't have any constraint, reactive power also doesn't have any constraint, as long as the apparent power is within the limit. What I mean by that means, if I have a selected 2.5 MVA transformer, I can put 2.5 megawatt with a unity power factor, or I can put 2.5 MVR with zero power factor, or I can put any megawatt with any MVR, which means any power factor combination, as long as the apparent power is less than 2.5 MVA. That's the real reason why transformer is rated in MVA, not really I mean, so say kilowatt. Probably means what say, is it mean like generators are rated in megawatt or kilowatt? Answer is no. For generators and motors, you need to ideally specify two parameters. Means what say, you have real power P, you have power factor, you have apparent power kVA or MVA. So out of these three, at least you need to specify two parameters. If you specify only one parameter, then generator or motor doesn't have any meaning, right? That's the second important thing. And looking at this, we have done means what say, though we call that capability curve of a transformer is a circle, means we have put up like, means when you go with the 100% loading of the transformer purely by real power, purely by reactive power, with reactive power but with an on-load tap changer. I mean, so how much real power you can load, how much reactive power you can load, that's what specified here. And I guess like image which I can probably zoom it a little more. Yep. Yeah. So means what, if we have like, this is 25 MVA, not really 2.5 MVA anyway. So 25 MVA transformer, you can go up to 24.75 MVA at unity power factor, but you can go only up to 23.73 MVA if the power factor is 0.9, right? And even for that, like your voltage is like 94.81 percentage, and same power factor, but if you are allowing the transformer tap to change to regulate this voltage, then probably means also you can load this transformer slightly better, like 23.838 MVA, right? So try this exercise with the different power factors, different grid voltages, then you will understand a lot more, right? So probably that's what I thought of conveying. Transformer rated in kVA because transformer doesn't have independent real and reactive power constraints. How much we can load purely depends upon many factors. That's what we put as a question. It depends on the grid voltage, it depends on the transformer impedance, it depends upon the transformer X by R ratio, it depends upon the load power factor, right? So, and these are all external factors. With respect to the internal factors of the, are probably means non-electrical parameters, which you can say ambient temperature, wind velocity, and previous loadings, etc. And I also request you to read something more on the transformer overloading, because transformers are capable of even loading up to uh, even loading up to 200 percentage, right? Please go through this standard IEC 60076 again. Means what's the loading of the transformer which is allowed, or overloading which is allowed. Your transformer can withstand the short circuit current itself for a 2 seconds, which means what say 100% load or 200% load, they can, I mean what say very well load up to means what say 200% or more, right? So you can just look at IEC 60076 and what's the loading of this transformer, and that I can leave it as an exercise for you on Sunday to probably get it more, or we can come back in the next week to talk more. All right. So is there any other questions? It means there would not be any coordination when MCCB used as an incomer. How this can take care? I'm not really saying that you don't need a coordination when MCCB is. So MCCB is there, still you need to coordinate, but that's where the difference comes. Like when you have a current limiting breakers and non-current limiting breakers, You can just google it with current limiting circuit breakers. Nowadays most of the molded case circuit breakers are of current limiting type, and they curtail this current much before this current reaches its peak. I guess in our video of the short circuit also we have talked about this. Right, you will get quite a lot of things, and probably means, let me put it in image so that it will be easy for you to understand. Right, this is a typical example. Yeah, this is an expected fault current, the sinusoidal, and probably if you have a current limiting features, means what, this curtails the fault current in less than 2-3 milliseconds. And if you have something like this, you may not reach even up to the maximum fault current. And probably means what, if you have current limiting type MCCBs in the outgoing feeders, then means what, see, the coordination is not to be done with an ETAP. Probably means what, say, you need to take the manufacturer simulation software or probably some other charts to validate the coordination. Even if MCCB is available, you need to ensure that is properly coordinated. Thank you so much, Charinath, for that question. And that's all from me today. And if there is any other questions, yes, I guess like these are the questions which we have already answered. ETAP tip which I have already talked about, and probably means one other one as like an ETAP video itself, like we have posted, that is done by Sargunan, one of our engineer, how to use this power calculator in ETAP. So I guess like you know where it is available, right? That's a power calculator. He has done a beautiful video. You can watch in YouTube or even LinkedIn, like we have posted that, which you can watch it. All good. Thank you so much for joining on a Sunday morning and spending a time. Hope the time spent is useful and you have learned something new. Again, we will meet not on coming Sunday, which means 8th. I am not available. So we will meet on 15th. Sorry, that is on. I am not available on 9th. We will meet on 16th May 2021. And for the skipping next week, I will try to upload some videos so that you can enrich that also. Yeah, thank you so much for joining. Have a great Sunday.